before we continue on, I'm going to just do something, a little thing on the side. I want to give you a couple ways to think about the mapping of surface data and how we can look at it. What are we looking at here? Here we registered our EPI data to some T1 or even to an EPI volume base that's in alignment with our surfaces. Then we mapped our data to the surface right then and there after the registration and did all our smoothing, blurring, all our smoothing and scaling on the surface, in the surface domain, and did the stats in the surface domain. Ran 3D volreg in the surface, 3D deconvolve in the surface domain. You can also have results in the surface domain and map them, results in the volume domain and map them to the surface domain, but they won't go through those pre-processing steps in the surface domain. So they might not be as nice, but you can do that if you want to. So I want to be able to show you that on the side. For example, how do these results compare with what we would have done in the volume? Even looking at in the volume and or mapping the volume to the surface after the fact. So I want to possibly just take a peek at that. So don't do this. I'll just try it on my own. And maybe if you're so inclined, you can do it yourself later. I'm going to CD into AFNI data 6/FT analysis again. I'm going to copy SO5 to, how do you spell S05? Copy that to SS. Fine, wonderful. And in order to compare these, remember we aligned our surface data with the current T1, right? So what if we did our EPI analysis without a TLRC block? Now it's the same analysis, but we're aligning to the current T1. That would put these volumetric results in alignment with our other results. So let's do that. Do we have any TLRC stuff? So let's get rid of that. Fine. I'm going to change my subject ID. We'll call this subject.ft.v.vol.orig. We'll call it orig space. Okay. So I'm going to TCSHSS. You are off and running. So that's going to do the same analysis as Tuesday, but not go to standard space. Otherwise, the same. And you let me just dump you down here. So now what are we doing here? So first of all, before we do anything else, let's just look at the results that we have. This image is actually one of the coolest things. I have seen in the little time I mess around with surface data. So we're thresholding based on the T-stat. Oh yeah, I didn't tell you the threshold. So most of you probably possibly have a bright green color overlay. You can drag this to some similar level, or you can even double click up here and type, let's say 3.0, whatever. So now we're thresholding our data at a T-stat and an AUD, an odd T-stat, where the auditory reliable T-stat is at least 3 or greater than 3. But the colorization is still at the -1.5 to 1.5 with this color map. You can choose a color scale here too, but that's the CMP line. I'll just mention that briefly. CMP, this is the color map choosing. But don't click on that because you'll lose your color map and then you'll have to find it again. This is an example where you might actually want to right-click on the CMP text to open up a window like this, and it'd be much easier to, oh, it doesn't help to stretch it. But you can at least page through these things, and it's an easier way to see all the color maps. Anyway, so are we all looking at basically the same image? Any trouble with that? what is cool here is this like upside down T or something here, the Y image. We have this strong intensity area, surviving threshold, that is anatomically sharp. It's not a big blob. You know, I'm not studying this in depth. I'm not looking at the time series. I haven't really spent much time with this, but at a glance, that looks really cool. I mean, that looks like it's so well defined anatomically. If we turn off the overlay, yeah, you can't turn it off quickly, too bad. But anyway, so you could, I was going to toggle it to see exactly what that Y corresponds with, but it's like right down here. Anyway, it just looks nice to see these. It's not a blob, you know. It looks like it's following the anatomy, so that it looks like, you know, some much more anatomically clearly relevant F key. Oh, fantastic! There you go. Foreground colors on and off. Oh, fantastic! There we go. So now we can play with that. So the background doesn't look. It's not following. You know, it's partly in the sulcus, partly on the gyrus. Anyway, that's what I wanted to do. That's great. Anyway, so something so sharp and strong looks nice, and it's probably not going to be that nice in a volume that's mixing all your tissue types together, and all your sulcal patterns will be mixed across Euclidean space. Okay, so with that in mind, I want to leave this here briefly. Oh yeah, you don't even have this data. So do I have this data? AFNI data. Okay, I do have this. So I downloaded, there's a SUMA MNI 152 2009. Actually, it's not called that on the website. It's called SUMA MNI 152 template, 2009 template. I don't know. I can send you a link if you care to do this. But so this is the MNI 152 2009 C template run through FreeSurfer. So that template, of course, is in that template space. That template is in FreeSurfer space. If you look at the coordinates here, if I click on the surface, it shows the coordinates here: 41, 9, negative 22.7. What does that mean in terms of my group of subjects? Nothing. These are original space coordinates. Node index 25,266. What does that mean across my subjects? That means this anatomical location across subjects. That does correspond across subjects. That node index is supposed to be the same place across subjects according to the FreeSurfer spherical registration process. But the XYZ coordinates don't tell you anything. So what if you wanted to put in your publications, well, where am I in MNI space? Fine, I can do a group analysis with this data, but the coordinates don't mean anything. I want the coordinates to mean something. Well, remember, like for this analysis, what is important? What is the part that gives us the group correspondence? The STD.60. The map icosahedron with the resampling of 60. So if we've done the using the FreeSurfer's registration and done the map icosahedron to invert those coordinates, and now we have our standard meshes, as long as that is working well enough, then we have nodal correspondence across any such surface, including our 2009 C template. So this, Paul Taylor just ran this through FreeSurfer a few days ago, and he put that out. So I downloaded the TGZ file. What is in there? .afni. I dumped it in my AFNI data directory because we use that for some things, but that's kind of irrelevant right now. It's got all these STD60 surfaces. It's also got the 141 surfaces. If you do a real surface analysis, you'll probably use those. It's a higher resolution. That's a more natural resolution. But anyway, it's got all this stuff. So
the macaque has also something similar, the macaque atlas.
the macaque?
Yeah, does it have something similar?
Well, you'd have to rely on having that spherical registration step done. So in these cases, if you gave free surfer macaques and the macaque cortical patterns matched the human patterns well enough, subject to that, you'll get.
But at least in Kieran, I remember that the F99 had a spherical map also. I don't know for the macaque atlas in the T99 that you guys have in Athens, if you have some correspondence also.
If we don't have one, we could possibly make some correspondence. If we sent it through the same software package and then subject to their spherical registration step, we should be able to do this. So you see, this is really powerful. We can any subject that you send through this same processing stream, subject to their registration, you get nodal correspondence. So I'm going to Rickar hist, wasn't there a hist file? Hist SUMA. So I'm going to set my subject directory to be, I'm going to set this sdir variable to be that MNI 2009 directory that has all the surfaces, and then run SUMA with the spec file that's in that directory and the surf file that's in that directory. What space is the surface volume in? MNI. The surface coordinates are all in MNI space. Wait, what directory am I sitting in? Oh, I'm still in the results, fantastic. So I'm still in I'm in the results directory. Let's look at the inflated surface. I'm still in that same subject results directory that was just created by the AFNIproc script. But now I'm looking at the MNI 2009C template, surface template in that subject results directory. So can't we Control S, load dataset, stats, open, what do we look at? The audit, the indices 4 and 5. We threshold to what, 3? Come on, behave. 3. We colored to 1.5. How do you spell 1.5? There you go. Same results now on the MNI template. If we click in the Y there, coordinates 43.31.5 versus 41.9, negative 22. The coordinates are drastically different. These coordinates are in MNI space. And there you go, piece of cake. No effort almost at all. So that's the power of having those icosahedron surfaces. You can just leap across subjects as long as they've run through that same mapping. One more thing. Our volumetric analysis is done. Let's see if I can handle what I'm doing here. So if we run AFNI-NIMH, so if we cd into this results directory, these are the volumetric results in original space aligned with this T1. It's the same T1 that we're aligned with in SUMA up here. So what happens if I run AFNI-NIMH here? AFNI-NIMH here should talk with the first SUMA created. That should be this one up here. That's the one that we ran the surface analysis with. So let's just test ourselves here. So I'm going to just look at their stats in AFNI first. So I'm going to set my overlay to be the stats, And let's look at the same stuff. Let's look at the auditory reliable beta weight, the auditory reliable t-stat, set the threshold to about 3. Scale the beta weight to 1.5. Okay, the same colorization. Now, do we talk? Come on. Oh, we need this volume here. ft vol. So I'm going to copy ft.surf results, ft.surf, surf vol aligned to experiment. I'm going to copy the surface volume here. AFNI needs the surface volume to accept the coordinates. So now I'll just lower this window. And let me set that to be my underlay. So now it has that data set. Should be on the bottom. Okay, one more try. Closed and opened. Force it, and there we go. So now we have surfaces in here. Now they are talking. So now, I messed up my threshold, but whatever. Let me just change my subbrick just to see. So now, what are we seeing in SUMA? Now the data in AFNI is being mapped to SUMA, according to that same volume to surface mapping. Actually, in this case, I haven't been picky with it, so this is merely using the midpoint between the white matter and the peel. It's just taking the intersection value, the volumetric value at the midpoint, not intersection, at the midpoint of the line segments between the white matter and the peel. So I didn't take the weighted average yet. Maybe just to very briefly show you I can click on Define Data Mode Plugins, Vol to Surf. I can do that. I can say use Vol to Surf, yes, map function av, just to show you. Node, number of steps 10. This is basically what we did before. Surf A 0, 1, I think that's probably right. Set and keep, hide that, and redisplay. So now we're using the same mapping. So now I'll go back to the beta weight, and we're looking at basically the same result. How about our y now? Not as pretty. I never looked at this before, so this is I didn't know how it would turn out. But you can see it's not as nice. And if we go back to SUMA, we can actually toggle between these. Switch data set, stats, SUMA, AFNI, SUMA, AFNI. So they're both in SUMA's hand now. It can switch between them. What is SUMA really looking at? Here SUMA is colorizing the numbers in the stats data set. When I switch to AFNI, SUMA is merely showing the colors that AFNI sends to SUMA for the nodes. So AFNI is doing the colorization in volume space, and AFNI is giving each node a color and sending SUMA colors, not values, just the colors. So the colorization should exactly match what we're seeing in AFNI. So the tints and stuff, the hues, things might be a little different from that, but clearly you see the statistics are a little different as well.
But so the threshold, you have to do everything in AFNI, and then you send the final result to SUMA.
Yeah, in this case, in AFNI, we're looking at the volumetric data. We set the same threshold, 3.000. The color range, 1.5, just like in SUMA. So that's negative 1 to 1 times 1.5, so negative 1.5 to positive. And so there's a colorization in AFNI. And we can click, if I right-click on there in SUMA, we jump to that location in AFNI. So here's the same area in volume space as we have in SUMA on this in the surface domain.
And if you change the threshold in AFNI, the projection of the surface automatically updates, or have to rerun?
Did you do any smoothing of the volume?
The volume did the same analysis we did before, except we didn't go to standard space. So we did the 4 millimeter full width half max blur. In the surface, we blurred 2 6 millimeters. In the volume space, we added a Gaussian of 4 millimeters. So they'll probably be comparable. But that would be a good point. The smoothing might be different, but it should be pretty comparable in this case.
One last one. If you do the analysis on the surface, can you do the opposite? Send now the results to the volume? So that
Yeah. We have a 3D, so the volume to surface mapping is done with 3D Vol to Surf. There's a sister program, 3D Surf to Vol, that will invert that mapping. That's pretty cool. So you're seeing in one case the analysis done on the surface, and again that was this case, and then you're also seeing the analysis done in the volume map to the surface for that same subject. Did the analysis in the volume in standard space, and that then mapped it to a standard space surface. How would you think that would look? Better or worse? Worse, much worse. At least with this subject, the surface is in the right place in the volume. And so the mapping from volume to surface is correct, except it was done after volume processing instead of after surface processing. So it's just really it's just the blurring that's different between. The blurring was on the surface rather than in the volume. That's really the main difference. But if you mapped standard space volumetric results to a standard space surface, the contours of the surface are not going to match the contours of that volumetric and anatomy. So then, however the contours happen to hit, if you do a good job with nonlinear registration, perhaps. But otherwise, the mapping is going to be much worse. So you would only do that to make a quick, pretty picture. So it's easier to if you want to map to a standard space surface, it's better to do it the way we did here, wherever the heck that went. Here, so here, this is the M&I surface, and in this case we have node correspondence. So we do the analysis in the surface, but we're using the node correspondence of the map icosahedron to show the result in M&I space. So a lot of different ways to look at this. And how would you run a 3D t-test now that you've done your analysis? We've got this stats left hemisphere NIML DSAT and right hemisphere NIML DSAT. How do you do a group analysis on this now? Same way as before. You just run 3D MIMA, LME, 3D t-test, 3D MVM. These data sets are fine. Remember, we're doing all of our work here was 3D t-stat on surface data, 3D calc to scale the data. Doesn't have to be volumetric because these are not, there's no spatial dependence to 3D calc. It's just at every location, do your calculation. So it's not blurring over space, so you don't care about your neighbors. So for these programs, you can use them with surface data, and that applies to your group analysis. What about clustering? Clustering is different. But performing the group analysis to get the t-stat at each location and the beta weight at each location, that's fine. So I think that's good for this part right here.
Can you guys both the hemispheres or single?
Say that again.
Can we visualize both hemispheres or single?
That's right. So this spec file was only for the left hemisphere, so that's all we're looking at. But there is a spec file with both hemispheres, so you could look at them both, or you could switch to the right hemisphere spec file. But the analysis steps, you see the analysis is done for each hemisphere, so the computations are separate, but the display can be together. So the regression matrix is identical between these. The statistical results everything is computed exactly the same, except instead of using the TLRC block, we have a surf block and map to the surface. And then the blurring is different between the surface and the volume. That's the only difference between these two methods.
I have one more general question.
Okay.
In the sagittal volume view of the brain there, you can see that there's activation. Yeah, you can see that there's activation outside the brain.
Yep. Mm-hmm.
And when using the surface view, are you more? You can't see that in the surface view. Are you more at risk to?
Definitely. In the surface, you are blind to such artifacts. If you have motion artifacts, if your results, like in the volume, if you've got results, what does a motion artifact look like in the volume? Many of you may have not seen it. It would be a statistically significant looking result that just follows the contour of the cortex. It doesn't really care where it is in the brain, it's just following the cortex. So the motion-based result is just dealing with motion correlated, with motion that is correlated to your regressors of interest. And so you get some result that just likes the contrast there, the tissue contrast, and but the location doesn't matter. So like this, you can, to some degree, this follows the whole cortex, but this is getting strong blobs in the visual area and the auditory area, so that actually looks okay. But anyway, so if you had a motion result, it's easier to see that, oh, that looks bad in the volume. But in the surface domain, everything looks beautiful. So it's more easy to be fooled in the surface domain, and that's one reason I suggest doing a sister analysis in the volume and just looking at them to see if there's something that you need to be interested in. Okay?
So when you blur on the surface, is here, this is the 6.0, this is a distance about the nose or the dimension?
It's the 6.0 millimeters is basically a Gaussian blur distance, but it's on the nodal mesh. So distances are not Euclidean, and they're not even straight because you've got to go along triangle edges. So 6 millimeters is kind of an estimate along triangular edges, and so that it's actually a more complicated computation to keep track of. So blurring on the surface is a little more difficult. And estimating the blur on the surface similarly. This is doing both because it blurs and estimates. So it keeps growing out until it seems like it's locally 6 millimeters all over the place.